Next, Johannes Klepsch from BMW will speak. Johannes chairs a working group in the Quantum Computing Application and Technology Consortium and leads the BMW IT Quantum Computing Initiative. His background is in mathematics with a PhD from TU Munich. Analyzing and comparing different quantum computing solutions is a challenging task for companies who want to experiment with quantum computing applications. He will present a concept for an application-centric benchmark method framework to foster the investigation and creation of application benchmark for quantum computing. Let's give a warm welcome to Johannes.
Great. Thank you so much for the nice introduction. Yeah, I'm here today to talk about QUARK. And as this has raised some confusion in the past, when I say QUARK, I don't mean the German Milchspeise, and I also don't mean the concept of particles in physics, but I mean QUARK as in the software framework that we use for application-centric benchmarking. Right, so my goal for today's talk is basically twofold. On the one side, I want to convince all of you that by using QUARK, you can make your life much, much easier when you are interested in running application-centric benchmarks. And the second target of today's talk is for all of you who actually do, code from time to time and are interested in running algorithms based on industry applications. I want you to go check out our open source repository and see if it can do something for you. Now, benchmarking is pretty much all over the place. I think we heard it in a nice panel before. We heard it throughout a couple of talks in the last 2 days. As a matter of fact, a PhD student in our team is currently at the IEEE Quantum Week in Washington for probably, most of you will know it, one of the bigger events in quantum. They accepted about 150 academic publications and papers and talks, and he said that he counted, and 15 out of those 150 talks have benchmark in the title, right? So it's fair to say that benchmarking is one of the games, and there are plenty of frameworks around, plenty of system level benchmarks, holistic benchmarks, and you name it. And so you might wonder, why do we need yet another framework, yet another concept? And I hope that again. I will be able to convince you that there is a place for QUARK, and that QUARK does fill this nice little gap in the middle. Right, so maybe before diving into more details, why is benchmarking all over the place these days? I think we all agree, and this is exactly what has been discussed so far, that for a nascent technology like quantum, right, like especially as an end user such as BMW, you're always wondering, how far is the technology really along? What can it really do? And you hear all of these startups such as Classic and many others who tell you, with our system, with our product, life is going to be so much better and easier, and the results going to be so much better. And at the end of the day, it's difficult to judge, right? You can't read all of the papers. You can't go into the depth of every of their products. So basically, a couple of years back, we thought, let's turn the game around. Let's define reference problems that we are, from an industry side, interested in, classical automotive type of textbook problems, and let's see what the community can come up with. We organized a quantum computing challenge back in the day, open sourcing these problems and asking for a community to contribute. And results were impressive, amazing. We got over 70 submissions and thought, okay, now let's try to, operationalize that a little bit, and thereby defined a QUARK, which is, as mentioned, a application-centric benchmarking framework and so much more. And basically the way this started is that also for our internal work, right? So if you're a student, for example, doing research on quantum computing algorithms, you try to submit your publications to nice journals, to nice conferences, and oftentimes reviewer will ask you, can I see the data? Can I get reproducible results? And this is tough, like building these data pipelines in such a manner that they are stable enough for you to be confident enough to give them out is a challenge, and especially for physicists who might not be the best software engineers, for example, coming up with something that is actually bulletproof in terms of making it stable is a challenge. And then once you came up with, say, a first version of your algorithm, and it works okay, but you want to somehow tune the hyperparameters a little bit, want to try out different versions of it. This is again super challenging because some of them might not be parameterized properly, right? You might do loads of errors by having to change hard-coded values here and there. So again, trying to professionalize that a little bit is something that is going to be so important in order to come up with reliable and trustworthy results. And this is why QUARK has value, and basically what it is essentially nothing else than this beautiful GitHub project. And we build it in such a way that it's like the core fundamental concept of it, it's modularity. So we want it to be as extendable and easy to use as possible. And basically, it's nothing else than a set of instructions of abstract classes that you can combine so that it fits your needs, right? One of the differentiating factors is, however, that the top class, so the top abstract class, will always be an application class. So we are very, we want to stress this application-centric notion of benchmarking in the sense that in that top application class, you will always have to define application-centric metrics that you're interested in, somehow specify the parameters that define your model, and so this application class is always going to be the top class. Everything below can be then structured according to the needs of the problem. We are also very proud to say that it is a community-driven project. So it started off as a BMW project back in the day. Now you probably won't be able to see, but the GitHub project has no mention of BMW anymore. We really want to be able to give everybody the possibility to contribute, to share the results, and it's working. So we got our first pull requests from outside of BMW. Several research projects are picking up, starting to use it. Different researchers also are trying to integrate their problems, their solutions to it, and it's getting there. Now, this was all a little bit abstract, I think, right? A lot of adjectives describing concepts. So let's try to make this a little bit more concrete. And for the remainder of the talk, basically, I want to go through two different application-centric benchmarks that we integrated in our application-centric benchmarking framework. And hopefully, you'll be able to see how this modularity plays out and what the value really is. And so the two examples are in optimization, where we use an application top abstract class, then a mapping class, then a solver class, and a device class, and then a machine learning example that obviously has different needs and therefore has an application class, a dataset class, a transform class, a circuit class, a library class, and then a training class. Okay, so let's go through these two examples and start off with the optimization problem. So the problem at hand is a problem that we also are working on in one of our funded research projects. It's a problem in combinatorial optimization. You can say what you want about combinatorial optimization, but it lends itself very nicely to come up with application-centric benchmark kernels, because normally there is a clearly defined metric that you try to optimize against. In our case, this metric is cost, because the problem basically is the allocation of capacity of our press shops. You can imagine that BMW has about 10 press shops throughout the world where basically these metal sheets are pressed. Yeah, so Presswerk. And so doors and hoods and all of these things are pressed there. And then the next question is, for assembly, there are different plants, and again, about 10 different plants throughout the world. And so the bottom line question is, where should we allocate our capacity for pressing so that basically the cost is minimized when we are actually assembling the cars at the end of the day. And this sounds like a pretty easy problem, right? 10 press shops, 10 factory plants. Whereas the challenge? Well, turns out that there is all sorts of constraints. Obviously, not every plant can press every part, and not every assembly plant can build every car. So there is a lot of constraints. As a matter of fact, when we first looked into this problem, I was a little bit shocked because we had 120 pages PDF document worth of constraints, just describing different constraints of the problem. So it's a bit of a complex problem. But yeah, we tried to somehow come up with real results of that real solutions to that problem. They don't involve quantum, to be honest. However, it lends itself very nicely as a textbook type reference problem to see where the technology stands. And so we used QUARK in order to come up with reliable data to see where we stand. And again, first defined our application class. And in that class, basically, the first thing that we do is to define the metric that we're trying to optimize against, which in this case is cost. Defined the different constraints of the problem, and parameters kind of describing the problem space. The more interesting class, to be honest, is the mapping class, and there you'll see that there's different options, right? So obviously you can put in as many options as you want. We started with a classical option, so a classical mapping of the problem. In our case, basically just a linear representation of the problem, and then a cubo representation of the problem. So a quadratic unconstrained binary optimization problem. Then we implemented different solvers, and here, again, different options depending on what mapping you have. You have to, implement different solvers. For the classic representation of the problem, we integrated, C-plexes, Gorobis, and the likes to get a good baseline. And for the cubo representation of the problem, we, used open source frameworks to come up with different solvers. And of course, QAOA and the likes are integrated here. And then again, depending on what solver you implement, you want to make different hardware sets available. This is why I was interested in the classic talk before, because it's very nice to have a way to map your solver on different hardware sets and be able to compare as well. So in this case, you can run it locally on your machine. You can use whatever AWS EC2 instance that you want, or say the QQuantum NVIDIA simulators hosted somewhere, or real quantum computing devices. And so again, all of these things are basically abstracted away through these different classes, yeah. And now, once you did all of that, implemented your different classes, you can go ahead and use the command line interface that QUARK will offer to you. Now, I recorded a little video, probably this is not going to be visible, so I'm going to try to quickly talk through that. Basically, what happens is that you get prompted to specify the different parameters that you want to compare. Say, I don't know, I want to compare a 10-qubit representation of a problem with a 15 and a 20 representation of the problem. I want to include that many parameters, that many hyperparameters. I want to use, I don't know, different solvers and different hardwares. Then this runs and compiles, and at the end of the day, you get a nice results CSV that basically stores all of your data. You get nice little demo representations and visualizations of your problem. You get a config YAML that basically stores all of your configurations of the problem. And yeah, somehow, if you want, even the Git footprint of basically the version of QUARK you used. So that basically it's a nice packaged up set of data sets that can really, trust and be very aware of what actually was used in order to create these data points. Second example, in machine learning, which is a completely different ballgame when it comes to trying to run these types of experiments. So the example that we used in this benchmark was generative modeling, for obvious reasons these days. Yeah, so basically example applications within BMW could be in generative design, obviously, but everything that involves synthetic data is obviously interesting here. This example is based, by the way, upon the work of a QTech working group. So I don't know if there's any QTech representatives here. I'm proud to wear the nice little thing. So basically, the algorithms and the likes were developed in one of our working groups, and basically internally within BMW, and then integrated it into QUARK to make again the data pipeline structured and trustworthy. So let's try to map this onto our different abstract classes. First, we define The application, in our case, the metric that we used as a benchmark metric was the QUARK divergence, so basically comparing the target distribution with your sample distribution. And also included generalization metrics, which is the key thing, right? You want your model to be able to generalize, otherwise creating synthetic data that is basically in your input distribution doesn't really help that much. Then we made different data sets available, different discrete and continuous data sets. The example that we see here is a very, very easy two-dimensional probability distribution that is in the shape of an X. So yeah, we start off with these nice little rim designs pictures, but at the end of the day, you know how it goes in quantum, you end up with a 2D version of a probability distribution that we then transformed using different metrics in order to be able to then map it onto different circuits. In our case, we implemented, again, a standard circuit and a copular circuit that will allow you, and I won't go into too many details, for the target distributions to be nicely uniformly distributed between 0 and 1, and you just structure, keep your correlation in a covariance matrix. And then we have a Qiskit class. And this is actually interesting because basically in our circuit class, this is just a set of instructions basically that we can then completely abstract away from the open source framework that we then use to actually run these circuits. Yeah, so basically the set of instructions could exactly the same be projected onto any other framework of your choice. Again, one of the powers that this abstraction, this modularization really gives you, right? So we could, for example, run a benchmark comparing the performance of Qiskit versus PennyLane while keeping all of the other constraints completely similarly. Yeah, in our case, we just implemented Qiskit for now and then use different training methods. So comparing here QCBM, so quantum circuit Bohr machine methods for training, generative, adversarial networks for training, and also implemented an inference class because at the end of the day, this is what you then want to see from your trained models. Yeah, and so basically the way this works, right? So you input a X shape, you give it to your discriminator, and thereby somehow train your model and end up at some point with a converged model that will then somehow be able to do something like that. So this is kind of depicts the training process, right? Starting from complete noise and at the end of the day, somehow then converging to a nice little X-shaped distribution. This, by the way, you can see that it's a 64 by 64 grid. So it's a 12 qubit chip because basically every of the 2 dimensions is discretized using 6 qubits, and every basically pixel is then one sample or one base state basically that you sample from. By the way, all of these results are published in the archive paper here. But one of our PhD students that is at IEEE Week is presenting that as we speak in Washington. Because one of the nice things that you can now do, right, to show some results finally, is to compare these things like how does your QUARK divergence improve when you increase the circuit depth of your circuit? Turns out it doesn't. How do different discretization schemes kind of compare to each other? And these are depicted by the amount of qubits here. One of the other results, and this is interesting because it kind of answers the question that we had before in the classic talk with respect to whether or not GPUs are quicker in simulating quantum circuits than CPUs, and I think the answer given in the last talk was no, they're not. I would contest that and say yes, there is a huge difference, especially if you're in that regime of 30 qubits that the classic colleague talked about. So basically what you see here is the execution time of simulators of the QQuantum, so basically exactly what the classic guys did, so the NVIDIA QQuantum simulator, if you execute it on the multi-CPU machines or on a multi-GPU machine. And you see that basically at the beginning, in the regime of, say, 8 qubits, the CPU are quicker in coming up with simulation, but the moment that we reach somehow the 18, 20 qubit regime, this is when GPUs outperform dramatically. And at the end of the day, so the 30 qubit kind of simulations, you have to do somehow like 1 billion a billion executions in order to make that happen, and you see up to a 300-fold speed up when running it on a GPU. This was run on 8 A100 GPUs, in case you're interested, and 265 CPUs. So it's a fair benchmark, and you do see that GPUs actually are very powerful in simulating quantum circuits. But this is not the moral of the talk. The moral of the talk here again, that this data collection that happened, is happening very, very easily once you're using the beautiful framework of QUARK. And to close this off, the community is growing. We have about 40 clones over the course of 2 weeks these days, 50 pull requests. We're cited 9 times, have 25 stars on our GitHub project, so it's getting there. Yeah, it's slow, but it's getting there. Summarizing, right? I hope I was able to convince you that you can very seamlessly come up with reliable data using QUARK. That it does facilitate the implementation of application-centric benchmarking. And with that, I owe you a QR code, as in every good presentation these days, after which you hopefully will be able to find the GitHub project. And I hope to get many more stars and many more pull requests over the course of the next couple of weeks. And thank you very much for your attention.
Thank you very much for your presentation. We still have 1 minute. Are there any questions from the audience? Okay, not at that moment. Maybe
who's gonna clone the GitHub project? By show of hands. 2. I will count. 3. I will count. Thank you. Sorry.
Okay, thank you.